Welcome, everyone. Good morning, good afternoon, or good evening, wherever you are. Welcome to PALS. Today, Nik Ruskuc from St. Andrews will talk about heights of congruence lattices of semigroups. Please.
Thank you, Peter. Hello, everybody, and thank you for joining in, either here or, as Peter said, wherever you happen to be. I've already had great 2 weeks here in Boulder, and I'm very grateful for you guys hosting me. And my visit is now coming to an end, but hopefully I'll be back before too long, I guess. And people might think it's a bit audacious to come to Boulder and tell you about height, especially if I come from Scotland, where the tallest mountain is about 1,000 meters. But hopefully I can entertain you a little bit. Don't worry, it's height of semigroups rather than height of mountains. Definitions are the basic concepts are pretty easy. The height of a poset, I'll talk about finite things today, so let's not worry about cardinalities and suprema and things like that. So by height of a poset, I will mean the length of a longest chain. So the biggest n, such that I can find n elements in sequence, each one being strictly greater than the previous one. And I will use this notation for it, ht for height. And just a couple of easy examples. So if I have a 5-element chain, its height will be 5. If I have the diamond, then the height will be 3. There are 3 chains of length 3 here. Or if we have a pentagon, then the height is 4. In some papers, people use this number -1, which would be like the number of edges, or like if edges of length 1, then kind of that would perhaps also be a natural notion of height. When we were writing our paper, great debate was had which way to go, and we opted for this one for a number of reasons, which are not particularly exciting, so we'll skip them. So this is the definition here, but somewhere in literature you might find this number -1. Can I get rid of that?
You can probably remove it if you want.
Like here, for example. So this slide is more or less what I wrote in my abstract, which Peter circulated a week ago. No, here we go. So somehow the starting point is a very nice paper by Cameron, Solomon, and Turrell from 1989, where they give a nice formula for the height of the subgroup lattice of the symmetric group Sn. And I'll show you the formula in a second. What Sn is for groups, Tn, the full transformation semigroup, the semigroup of whole self-maps from the n-element set into itself, is for semigroups. So one might say, okay, what would be the sub-semigroup height for Tn? And this question was addressed by Cameron, Gadulo, Mitchell, and Perez in 2017, and they obtained an asymptotic formula for the height of the sub-semigroup lattice of the full transformation semigroup. I'll show you that formula in a second as well. However, what is subgroup in group theory can be interpreted in semigroups in 2 ways, and I'll say a little bit more about this in a second. An obvious analog is sub-semigroup, but another obvious analog is a one-sided congruence, or if you want action, or if you want a transformation representation. And so from that angle, one might say, okay, maybe we can view an analog of Cameron, Solomon, Turrell result by asking what is the height of, I don't know, left congruence lattice of a semigroup or a right congruence lattice. Trying to pursue this question, a team of us, coming on the next slide, have developed some kind of general theory that applies to all semigroups, certainly to all finite semigroups. Doesn't always give you a formula for the height. Sometimes it just gives you a lower bound. But in a great many examples, including the full transformation semigroup, it gives you a precise formula for the height of one-sided or two-sided congruences, depending what you plug into the formula. And I want to tell you about this result. I want to tell you not necessarily how it is proved, but what the components in the result are and how one can think about it. And I want to tell you how it applies to Tn. So that's my plan for today. And I'm happy to be interrupted with questions either in the room or from the world. Here is the team. These are the people who have worked with me on this project, and we've had a lot of fun with it, mostly in St. Andrews, but also a bit in Sydney and a bit in York. Matthew Brooks, James East. Matthew is currently in St. Andrews. James is always in Sydney. Craig is currently in York, and James Mitchell is in St. Andrews. And we've got a paper out of it, which is currently being considered, and there is a preprint on archive that you may have a look at if you want to take this further. Okay, so let me now go through my program, but a little bit more kind of steadily. Okay, so subgroups. Here is the result of Cameron, Solomon, and Turrell. This is the formula for the height of the subgroup lattice of Sn. And it's a pretty formula, but what I want you to carry from it is that this number is linear in n, maybe a bit less than linear in n. The little bits and pieces around it are good fun. Not so much the integer part. I mean, that's integer part, but this Bn is kind of quite magical. It's the number of ones in the binary expansion of n. It just comes up. The proof is actually quite complicated for, like, you might think that a simple formula like that will have a simple proof, but it doesn't. It's an inductive proof, and it uses classification of finite simple groups in quite a substantive way in a couple of places. And maybe another thing that I would like you to take from this slide is that compared to the number of subgroups of Sn, the height is tiny. So this somehow tells you that the lattice is quite short and very wide. This is an estimate of the number of subgroups of Sn by Pieber. And I have a memory that one of the group theorists in St. Andrews told me that either this has been proved to be accurate or that the correct number has been calculated. But as I was preparing this talk, I couldn't quite find the reference. So I don't know. But okay. Subsemigroups. Here's the formula. It's not really a formula. It's just a lower bound. I'm not going to read that. It's pretty big. Just for reference, n to power n is the size of the full transformation semigroup. Once again, for people who haven't been so exposed to semigroups, full transformation semigroup is a fundamental object in semigroup theory. It's a very simple object to think about. It consists of all mappings from the set 1 up to n into itself. The operation is composition. So it's like permutations and composition, except that you can send lots of things into the same place. No inverses.
E is always constant.
Yes. The basic idea, so basically you want to construct chains of this sort of size, of sub-semigroups. And the basic idea in the paper is to look at each principal factor. Okay, so I'll say a little bit more about this, but this is too much semigroup theory, too early. But you take all mappings in Tn of a fixed rank, and you consider that as a sub-semigroup. It isn't a sub-semigroup because you can multiply two things of rank 5 and get something of rank 3. But when you get rank 3, you say that's 0. I don't care about it. So you look at all elements of a certain rank, and when multiplication takes you out, you call that 0. That's a principal factor. So what they do is they take each principal factor in turn and identify a large 0 semigroup in there. And 0 semigroup is a semigroup where any two elements multiply to 0. And that has an awful lot of sub-semigroups because you can just keep adding one element at a time and get a long chain of height size of the semigroup. Right. That's basically the idea. And then you count. And they also give an estimate about the total number of semigroups, so you can, again, kind of compare. Okay, so that's the background. That's motivated us to ask the question about one-sided congruences. Let me now lead you towards one-sided congruences in semigroup theory. I'll go back first to the elementary group theory that we teach to our undergraduates. So let me have a group G and let me have a subgroup inside G. Left cosets. Let's look at left cosets. Left cosets partition the group. And therefore, there is some kind of equivalence relation going on there. And the equivalence relation is this one. X is related to Y if their quotient, like this, X inverse Y, is an element of the subgroup. This equivalence relation has an additional nice property. It's invariant under the left multiplication. It's not necessarily a congruence. It's not necessarily invariant under the right multiplication, unless H is a normal subgroup, but it is invariant under the left multiplication. Equivalently, you can say G acts on the set of left cosets by pre-multiplying, by left multiplication. And not only that, but in fact, this family of actions exhausts all transitive actions of the group up to isomorphism of actions. So you get something quite significant by viewing subgroups in this way. This property here is the defining property for what we call left congruences in semigroups. So partition by cosets, partition into cosets into left cosets by a subgroup would be a typical example of, maybe not a typical example, but it would be one of the examples, motivating examples of a left congruence on a semigroup. Here's the definition. So this time I have a semigroup and I have an equivalence relation on this semigroup. And I assume that the relation has left compatibility property, so it's stable it's invariant under the left multiplication. If that is the case, then S acts on the set of equivalence classes of this equivalence relation by left multiplication. That's precisely what this condition gives you. And if S happens to be a monoid, then this describes all there isn't an accepted term. I would call it probably monogenic. Maybe you want to call it cyclic actions. What this means is that, so monoid acts on a set, and the action is cyclic if there is a point in this set from which you can reach all the other points. And clearly, actions of this type have that property because you can take the equivalence class of the identity and that will take you, from there you can reach everywhere. So that's what becomes of transitivity in the absence of inverses. Okay. But somehow the important thing is that all actions, like in the same way as in group theory, a group action always splits into its transitive components. In the same, well, it's not exactly in the same way, but in a similar way, you can view a semigroup action as, or monoid action as being composed of these cyclic actions. The difference is that some of them may intersect, so you get some kind of amalgamation going on as well, rather than having just disjoint actions. Okay. I assume somebody will alert me if there is a typed comment or something of that sort. Yeah. Okay. So here is the situation that we have now. So we have the group world and we have the semigroup world. And in the group world, we look at the fundamental concept of a subgroup. And of course, it has the analog of sub-semigroup in the semigroup world. But it also has the analog of a left congruence. And then, of course, there is a concept of right congruence because unlike in group theory, in semigroup theory, left and right are not the same. They're not. Semigroup acting on itself on the left doesn't look the same as semigroup acting on itself on the right. Okay. For the moment, I will concentrate on left congruences, and then at an appropriate slide, I will tell you this can all be done for right congruences as well. But we'll just to keep things as simple as possible, we'll talk left. The set of all left congruences on a semigroup S forms a lattice, an algebraic lattice, a finite lattice in our case, because we are talking finite here. I will denote this lattice by L-cong for left congruences. What I told you before, left congruences of a group is the same thing as subgroups of a group. So the lattice of left congruences is isomorphic to the subgroup lattice of a group. Nothing of the sort holds in semigroups. The link between sub-semigroups and left congruences is worth investigating, but it's weak at best. And the guiding question for our work, and therefore guiding question for my talk today, is what is the height of the left congruence lattice of the full transformation semigroup? Some long time ago, they sent me on some training course for lecturing. That's like after I'd been lecturing for about 15 years. And they told me I have to drink water, very important. And then they asked me whether I pay attention to flexing my knees when lecturing. And I thought, no, I can either lecture or I can flex my knees, but I simply cannot do both. So I've adopted water, but knees are still a problem situation. Okay. Let me change the point of view just slightly and view these actions, which I actually haven't really defined for you. I just kind of skated around them a bit. Let me tell you how to view them as unary algebras. And Keith said more about that in his lecture last week. So left multiplication of the semigroup on itself can be viewed as a unary algebra. So you have one operation per element of the semigroup, and that operation translates every element of the semigroup into its left translate, AX. So maps X into AX. So you have a bunch of unary operations, and that's an algebraic structure. That's an algebraic structure which is very different from your semigroup, which has one binary operation. So I will invent a different name for this. I'll call this, it's not really not very good name, but somehow it seems to have been accepted in semigroup theory. So this unary algebra of S acting on itself on the left is denoted by SS, where S is a left superscript. Okay. And from this point of view, left congruences of a semigroup, which sound like a slightly artificial concept, become nothing other than simply congruences in the algebraic sense of this unary algebra. Okay. So I want to tell you, let's try, no, this is not good. Okay.
It will vanish. Put it at the bottom.
Put it. Ooh. Okay. So let's do something. So let's think about a unary algebra. And well, a single unary operation, you can view it as some kind of graph. It sends X to f of X, so that you can put an arrow, and if you have all these, that would be like a unary operation. But now you have a bunch of unary operations, so it's like a graph in which edges are colored in several colors, one per operation. And there are some properties underneath, but let's not worry. There is a graph lying there. And this graph, I can break into strongly connected components. A strongly connected component would be a maximal subset of vertices so that I can go from A to B and back for any two vertices. So any digraph decomposes into an acyclic graph of strongly connected components. Let me introduce, so I'm now going to take a connected component, a strongly connected component, and turn it into an algebra. But again, if I'm in a strongly connected component and I apply one of my functions, I can drop out. But the point with the strongly connected components is once I drop out, I cannot go in. So I may decide to ignore dropping out, call it 0, and when I reach 0, I just loop there. So that's what my new symbol 0 is. And now I take the strongly connected component, I add new element to it, and I define operations precisely as I told you. And I get a new unary algebra. Generally speaking, I will get, so this algebra will have the same signature as my original algebra by definition. It may have different properties than my original algebra. But the important thing for me is if I start with a semigroup action, and if I do one of these things, I will again get a semigroup action of the same semigroup. And now you can say, how does the height of the congruence lattice of my algebra relate to the heights of these strongly connected component algebras that I've just defined? And a relatively easy inductive argument shows that this is the case. And I wouldn't like to worry too much about this minus k here. That's an artifact of how choices had been made at the beginning. What I want you to remember is that height of the congruence lattice is the sum of the heights of the components. Having told you to forget about k, remember it just a little bit longer, just to note that if these strongly connected components happen to be simple, then I would get a really nice formula, which would just say k. Because I would have a bunch of 2's here, and then I would subtract k, and I would get k. Not so important because my actions will not be simple, but it is important because something else will be simple. So this is just to bring simplicity into the story. Okay.
This proposition was for arbitrary unary algebra.
Yes.
So they don't have to have
No.
count.
No. Yes. Okay, so now I go back to my semigroup and to its action on itself. I want to apply the previous proposition. So I need to ask, what are the components in this action? The components are something that is well known in semigroup theory. It's kind of daily bread and butter of semigroup theorists. It's called Green's L relation. And there would be more Green's relations, but only one of them on this slide. It's called Green's L relation. It breaks the semigroup into L classes. Here is the definition. Two things are L related if and only if they define the same principal left ideal. So very natural definition. And you can, if you work a little bit in your head, you can see how that relates to strongly connected components, because this equation says I can go from x to y by multiplying, and also I can go from y to x by multiplying. So I can now, for each L class, I can form this bar construction. They're my strongly connected components, so I can associate the barred structure to each of them. As I told you, they are actions as well. And I just plug it into the formula and I get this. Okay, and as I told you in the previous slide, wouldn't it be nice if these things were simple, because then we would be done. But they're not generally. So let me try to indicate why. So for this, I will unfortunately need, I don't know about unfortunately, I will need a little bit more of semigroup theory, but more or less this is where we will stop. So all Green's relations on a monoid. So we have seen relation L. You can anticipate relation R, the same thing, but on the other side. A very easy exercise. Relation R is a left congruence. Relation L is a right congruence. Slightly mind-bending because of left-right things, but important. H is the intersection of L and R. And D is the join of L and R, which happens to be their product, their composition. Which is, like, on one hand, very lucky. On the other hand, if you look at the definitions, it's really rephrasing of associativity. So, in other words, nothing deep about it, but it's like super important. And J relation is the same as R and L, but for two-sided ideals. And again, something that is less obvious and quite neat, J is actually the same as D when the semigroup is finite. And for a lot of infinite semigroups, but not for all infinite semigroups. And again, important noting, H, D, and J are not congruences, not left, not right, not two-sided. So in the world of Green's relations, all I have is this: L is right congruence, R is left congruence, which is important. Okay. So remember where we are left with our kind of going towards some kind of formula. We have got this formula, and we want to look at a single L class, and we want to ask, what can I say about this height here? Okay, so let's take a single L class in a semigroup, in a monoid. Every time I say semigroup, you think monoid. There is identity. It's much simpler that way. And as I told you a couple of slides ago, it would be really nice if L bar was simple. But you can see that L bar, generally speaking, will not be simple because R was a left congruence and H is L intersection R. And if you put all that together, you will, so a single L class is cut up into little H classes. And because R is a left congruence, this will be now a left congruence for the L class. And 0 doesn't matter, the element that I joined, because if I drop down there, I'm dead. I stay in 0 and don't move anywhere. Okay, so we now have this single L class. It's cut up into H classes that identifies some congruence on L in general, in a general situation. So L itself is not going to be simple. But let's now think what more is happening there. So let's now think about a single H class in a semigroup and in an L class. One of the basic facts about structure theory of semigroups is if H class contains an idempotent, then it's a group. And for our context, if this happens, then the congruence lattice for my L class between the diagonal, between equality relation and delta H relation is precisely isomorphic to the subgroup lattice of the group H. So I now identify a large portion of my lattice, which is isomorphic to the subgroup lattice of this group that I have found, if I was lucky, and found an idempotent. So now I will repeat my previous statement, but in a more complicated way. I hoped that L would be simple. It wasn't because of HL. I've now dealt with HL. I've translated it into groups. Wouldn't it be nice if what is left of L, when I factor out H, wouldn't it be nice if that was simple? Sometimes it is, sometimes it isn't. But in all the examples that towards the end I will show you, it happens to be. It's just an artifact of having lots of mappings or lots of linear transformations or lots of something so that everything possible can happen. And if that happens, then the height of my congruence lattice for the structure L bar will be the height of the subgroup lattice of this group that I have found somehow in there, plus 1. And at that point, I will be quite happy if that happens. Okay, let's now put it all together and get the formula. One more semigroup theoretic fact. So I'm now climbing up. I went semigroup, L class, H class, got something local. Now I want to go up. And as I go up, there is one more trick that we can do. Remember, the D relation was join of L and R. So a typical D class will have lots of L classes in it. They all happen to be isomorphic. Just the basic fact of semigroup theory. They're all isomorphic as acts. Therefore, I don't need to go into every L class of my semigroup and ask it, what's your height? I can just do for 1 per L per D class, and then multiply by the number of L classes in the D class. So unfortunately, well, fact of life, one of these D classes will be the minimal two-sided ideal of my semigroup. The L classes in this require a little bit of extra attention, but they're not going to get it here because it's a little bit of a distraction and it caused some headache because it was just fine-tuning the formula. So, and it's not really essential for the viewpoint. Okay. So now we got down to the L class. We got a formula for the L class expressing it in terms of height of subgroup lattice of some subgroup. We said we only need to take 1 L class per D class and possibly fiddle with the minimal ideal. That's what we said we need to do. And this, it leads to this formula. So there are two cases. Two cases correspond with me fiddling with the minimal ideal. But basically what they say is go into every D class, count how many L classes there are in the D class, Mi. See if you can find an idempotent in D class. And if you can, there will be a group there. Find its subgroup height, multiply by Mi, and sum over all D classes. And there are, as I said, two cases depending on what's going on in the minimal ideal. Let's apply that to the full transformation semigroup. So I now want to do everything I've done theoretically so far, but I want to do it concretely. So I have Tn. I need to tell you what Lr and LRD, what the Green's relations are, okay? They're all characterized by some numerical, by some combinatorial parameters of mappings, specifically image, kernel, and rank. Image is image, kernel is a binary relation, rank is the size of the image, which is also the number of equivalence classes in the kernel. And Green's relations are determined by these parameters as follows. To be L-related means to have the same image. To be R-related means to have the same kernel. And to be D-related, which is the same as to be J-related, is to have the same rank. To be age-related means to have the same image and the same kernel. I didn't write that out. So D classes correspond to ranks. There are n possible ranks in Tn, 1 up to n. Each D class contains idempotents. It contains lots of idempotents. Incidentally, that makes Tn into a regular semigroup. Not important here. If you have an idempotent of rank R, then, well, it has a kernel and it has the image. To be the idempotent, the image has to cross-sect the kernel. A little manipulation, you can convince yourselves. That means that the things that correspond to, that are in the H class of this idempotent look like bijections on an R element set. That means that that little group is isomorphic to the symmetric group SR. So Tn has lots of subgroups all over the place. They're all symmetric groups, but they're all symmetric groups of all sorts of ranks. First, Sn itself, that's the group of units, then Sn minus 1, then lots of copies of Sn minus 2. Keep going down. At the end, you get S1, which is the trivial group, which is what you get on the level of constant mappings. Okay, and Cameron Solomon Turrell will tell us what the height of SR is. All the other ingredients we have, we can do a bit of combinatorics, and we get this formula for the height of the full transformation semigroup. Height of the subgroup lattice of SR is here. That arises from the part of the formula which it said height of the subgroup lattice of age class. N choose R is how many L classes I have in the D class of elements of rank R, because they are elements of image size R. So the question is how many different image sizes, how many different images of size R I have? Well, that's the number of subsets of size R, which is N choose R. And you get this formula. You can do everything on the right, as I promised. I'm not going to write it out. I'm not going to write the general formula. It looks exactly the same as the one for the L class, for the left congruences. But the combinatorics is different for the full transformation semigroup. In a D class, the number of L classes and the number of R classes are not the same. If you want to count R classes, you need to count kernels of rank R. And that's done by Stirling numbers. And so you get a formula that looks like our previous formula, except that for instead of binomial coefficient, you get the Stirling number. And you have this little 1 here because there is a difference in the minimal ideal. So that's my 2 cases in the big formula, but I said I didn't want really to dwell too much on that. That's all there. As I told you, you can do this for two-sided congruences as well. How? Well, there is a little trick there. I mean, it's not a trick, but when I say it, it almost sounds like a tautology. For something to be a congruence is equivalent for it to be both left and right congruence. That sounds like a definition, but it isn't a definition, because the definition to be a congruence is to be compatible with multiplication. And it is something that needs to be proved that that's equivalent to being left and right congruence. It's not hard, but it needs to be seen. Once you've done that, it means that two-sided congruences can, or congruences can also be viewed as congruences of a unary structure, where you take both unaries on the left and on the right. And so you can run through the same theory. You can get a formula. This time, strongly connected components will be precisely D classes, i.e. J classes. So you will be just counting 1 per D class. For your subgroups, this should say age rather than gamma R. For our H classes, you wouldn't count subgroup lattices, you would count normal subgroup lattices because you're now doing congruences. And then you have a bit of a mess because of the minimal ideal subtleties. How does that work for the full transformation semigroup? I haven't run out of time, right? Well, I need normal subgroup lattices for symmetric groups. Well, that we know. They're all 3-element sublattices, Sn, An, trivial, something we proved to our undergraduates, except for 4 and then 1 and 2, right? But from 5 up, very uniform just 3 congruences. If you plug this into the formula and do the calculations and see what happens in the minimal ideal, you will get 3n minus 1, which is a nice number. Well, it's a number. But one shouldn't get too excited because the actual lattice of congruences of Tn is known and has been known for a long time. It's a beautiful result of Maltsev from 1950s, which has spanned a whole separate strand of investigations in semigroups, and there are lots of papers of about finding congruences of this or that. The point is, the congruence lattice of Tn is precisely a chain of length 3n minus 1. So, but at least it's nice to know that the formula was correct. And I will be wrapping up now. This is a table of nearly all semigroups that we considered. The first 4 are various semigroups of transformations. Full transformation semigroup is what we ran with in this talk. Following it are partial transformations, where you allow undefined images. Symmetric inverse semigroup, partial bijections on the set 1 up to n. And ON, the semigroup of order-preserving transformations. This is a doubly indexed family of linear monoids. So Q by Q matrices over a field of order n. Field of order P to the n. And then the next 3 are partition monoids, which people have heard me speak about, some people, but we're not going to enter into this here. Just another interesting family of monoids and their submonoids: partition monoid, Brouwer monoid, and temporally Lieb monoid. And this final one is dual inverse symmetric monoid. I'm not going to say anything about that. And for people who like numbers, here are some numbers for what they're worth. And let me leave you with some observations or questions. The theory, you will have noticed there was one point where I said, maybe you will be lucky and you will find an idempotent. And then we were lucky, and in all these semigroups, there are lots of idempotents. But that doesn't have to happen. The theory works perfectly well without idempotents, but there is a device where for an arbitrary H class, you can associate a group, even if it isn't a group. It's called Schutzenberger group, and it plays the same role. And you just plug that into the formula. However, there were other assumptions, most notably that L factored out by H was simple. That is something that really doesn't happen, and that cannot be replaced by something else in the formula. So in general, our approach gives you a lower bound. In fact, the height can be very far from this lower bound because there are semigroups where all relations are left, right, or two-sided congruences. In which case you get the lattice of all equivalence relations, and the height of the lattice of all equivalence relations is the size of the set. So we also know that there are semigroups that are strictly between these two, the lower bound and the upper bound, which is the size of the semigroup. Free bands, whatever they might be, are an example. It's a result by Matthew Brooks. We haven't found the right form for it or the right way to think about it. At the moment, it's sitting on its own. We don't know what to do with it, but it's a lovely demonstration by Matthew. Maybe if people want to look deeper into this, my instinct is to investigate possible values in this range. In particular, I'm quite interested to know whether there are phase jumps. For instance, it seems very plausible to me that if the congruence lattice is not all equivalence relations, then it has to be much smaller straight away. That it can't be kind of a few less than that. Just my intuition. In which case, I would hope that the height gets much less than S. Instead, that they don't know actually where to go or how to move. And then also something that I realized as I was writing this talk that we haven't addressed when we were working on this. I don't know of any sensible estimate for the number of left or right congruences for Tn. And that might be interesting also to look at. In particular, a few computer examples that we produced for T3, T4 indicate that it's again quite short and quite wide, the lattice. But we don't have right estimates. And this is where I will stop, and thank you very much for listening.